I'm Randy Packer. I am a senior manager at DreamWorks, and I want to thank you for coming to this talk on the Arras computation framework. I mentioned this in my talk yesterday. This presentation was supposed to be actually a colleague of mine, Mark, who unfortunately couldn't make it, so I'm going to give it. I'm not exactly as well advanced as he is on Arras, but I am pretty comfortable with it, so I'm happy to be talking with you today. Arras, by the way, I'll just mention, is part of the technology that we open sourced with MoonRay and is available at openmoonray.org. All right, so I want to take the opportunity to acquaint you with the amount of compute or rendering that goes into making an animated film. First, I'm going to change my glasses so I can read. Along with the artist's hours. So this level of compute and complexity that we face poses some challenges that we address explicitly with Arras. And let's briefly touch on what it means to render ray-traced images. So modern ray-traced rendering can take many hours to complete for a single frame. Adding more power to this issue means faster images and thus the opportunity for more artistic iterations. And with a very scalable renderer like MoonRay in combination with Arras, we can grab more cores and therefore get faster renders back. So what is our challenge? Essentially is how do we get more cores than are available on a single workstation so that we can render faster? And of course, the answer is with Arras. What exactly is Arras? First of all, it stands for Animation and Rendering as a Service. So I mentioned that this is not the MoonRay computational framework. This is the Arras computational framework. So we use it to run a variety of computations, rendering of which is one of them, animation is another. In terms of scalability, we've used Arras on hundreds of machines and thousands of cores. We've integrated into a number of the most prominent digital content creation tools, or DCCs for short, like Maya and Katana and Houdini, etc. And it's a bit like having a 1,500 core workstation in your hands. Awesome power. So let's get into it. Let's start first without Arras, where the user has a DCC, like Maya or Katana, and a renderer happening on a single box. In this example, with 36 cores available and shared, there are 36 cores available and shared between the DCC and the renderer. I don't know if that clicked through. Okay. Now, when using Arras, each client application makes use of it through a client library. To obtain a rendering session, the client makes an HTTP request to the coordinator service, which then tries to allocate available resources in the Arras pool. If allocation is successful, the coordinator responds with a network address of one of the nodes allocated to the session, called the entry node, and from that point on, the client only talks to the entry node, which communicates with all other nodes allocated to that particular session. This makes Arras scalable to the total number of active sessions. And notice that with Arras plus 3 render computations, we increase the render speed by 3x. Multiple Arras clients can connect to the Arras core services and use nodes in the available Arras pool. And any given single Arras node can run multiple computations for the same or different clients. Here's another illustration of the power of Arras to show the speed gain. And I want to note that this is definitely not a logical diagram of coordination and communication between the nodes, but simply very naively demonstrating the speed gains that we achieve. Local in this case means that there is a local Arras session running on the same box, and there are 36 cores shared between the DCC and MoonRay. In this example, the image takes about 5 minutes to render. However, crank up an Arras session, grab 12 hosts with 36 cores each, and you get to 432 cores. The merge and distribution is done on the local box, and in this example, rendering the image takes less than a second. In fact, it's a little bit closer to half a second. Let's talk about the need for Arras in a little bit more detail, or how we use it at DreamWorks. So an artist works on keyframes, and as they make adjustments, They quickly see their results as they rapidly iterate, thus saving the artist time, which translates into a higher quality overall for the movie. Walk-bys are when a CG or a VFX supervisor literally walks by an artist's workstation to see a shot or make a suggestion. At that point, artists can grab more nodes from Arras so they can iterate even more quickly when pairing up with supervisors. I'd like to call this pair painting, but nobody at DreamWorks calls it that. That's just me. It's common for artists, particularly leads, to have multiple instances of the same application running. An artist may run 2 or even 3 Maya sessions at the same time so that they can play and experiment with different versions of the same frame. In the past, they may sometimes ask for a second, expensive workstation to run the applications. Arras can save that effort by moving the rendering off of the artist box and saving considerable resources. In this example, a single artist has 2 instances of a DCC running, each with its own Arras session, and thus rendering 2 different scenes. This avoids the common need for artists to launch applications multiple times and switch back and forth. In this final workflow, we're going to look at multi-context rendering with Arras. And with this workflow, the artist can see the effect of every edit on multiple lighting setups or multiple shots in a sequence. I'm going to show a few demos here. This next one, if you were at the MoonRay's session yesterday, I also showed. And in this video, we're showing asset development under multiple lighting conditions in a single session using Arras. So it can take several seconds to transfer the scene and asset data to the back end and distribute to the nodes. However, once we get going, we get fast delta updates as we pan the camera around and we change radiance values. And the artist can see and manipulate the asset under 4 lighting conditions at once. Daylight, in this example, it's daylight, overcast, dusk, and night, to ensure that the asset, the van, looks good under all lighting conditions. So to further illustrate that, the user wants to see 4 live renders, but their machine doesn't have the compute power to do that. Using Arras, they can offload the work to multiple pull machines, making the workflow possible. So let's show some more examples. In this first example, we're going to see the artist in a lighting session with just MoonRay and not connected to Arras. There are 95 virtual cores shared between the lighting tool and the MoonRay renderer. And the artist is manipulating light position and radiance values in the scene. So this is 1 renderer, 1 session, 95 virtual cores. In this second example, the artist is now connected to the Arras pool and is running 1 context, in other words, 1 frame, being served by 11 render computations with a total of 1,045 virtual cores for rendering. The artist is again manipulating light position and radiance values in the scene, and this is obviously quite much faster. So 1 context, 11 computations, 1,045 virtual cores. In this third example, the artist is again connected to the Arras pool, but this time is running 6 contexts, in this case, 6 viewpoints of the same frame, with each context being served by 2 render computations for a total of 1,140 virtual cores for rendering. The artist again is manipulating camera position, material properties, and light radiance values on all as well as some of the contexts. So 6 contexts, 2 computations per context, 1,140 virtual cores. We've developed and run Arras as a local cloud service and ran it on major cloud providers as needed to punch through our on-prem capacity in order to meet key deliverables. In order to minimize packet size and reduce latency to the cloud, we do a couple of key items. 1, we use a highly delta encoded codec that we developed called progressive frame message. And 2, we process a partial image at each user-defined frame per second rather than processing the entire image at once. The messaging protocols are also designed so that higher message latencies cause greater delay between making a change and seeing the result, but don't result in a breakdown of the system, which would occur if they had not been designed to be fully asynchronous. Arras can receive notifications from the cloud provider that a node will shortly be withdrawn from our allocation, in other words, a spot interruption, which can happen in lower cost cloud plans. Arras will then shut off the affected node and shut it down gracefully, and can checkpoint the frame in progress to be resumed later rather than waiting for a node to fail. We've tested our scale up to 6,000 cores, and we saw linear speed up with the increased core count in all of our tests. In this fourth example, the artist is connected to an off-prem Paris pool running in the cloud, running 9 contexts in the Azure US West region. Each context is rendering a different shot or a different frame within the same film sequence. And each context is being served by 11 render computations for a total of 6,237 virtual cores for rendering. The artist was manipulating the environment light of the sequence and the light radiance values. Again, 9 Oregon contexts, 11 renders per context, 6,237 cores. As we've shown, MoonRay multi-machine rendering with Arras is powerful and scalable. In our pursuit of better efficiency, optimization is very important for us. However, it can be difficult to find bottlenecks in multi-machine environments, and it's also hard to simply debug parallelized multi-machine rendering. To ease that burden, we provide a few solutions. InfoCodec, which we developed, provides a mechanism of sending string-based information between nodes in a heavily delta-encoded way, and this minimizes packet size and latency. Shared memory footmark provides a solution to save the structured string-based information to the shared memory in order to keep the runtime debug information from unexpected segmentation faults with minimum runtime timing overhead. And the telemetry overlay provides a real-time visualization of the progress of distributed rendering, along with key information on network I/O and CPU memory utilization to make it easy to see what's happening on different machines. And I'm going to demo that right now. So here, at first, we see that the client, Pearl Diva on the left, is locally reading in the data from a large scene called ALAB, open source by Animal Logic. And this scene data is 2.6 gigabytes, quite large. Then the client starts sending the locally read data to a dispatch node called Teal Pond. We speed up the video 4 times as the data transfer can take some time. Now that the client has finished sending the data to the dispatch node, and therefore the dispatcher starts sending data to each of the MCRT nodes, of which there are 4 on the right, as seen on the right. Note that 3 of the nodes are receiving the data very fast. However, one of the nodes, the second one from the top, Ruby Minute, is on much older hardware and is receiving the data quite a bit slower. The blue graph indicates 1 gigabyte per second speed, and the gray graph indicates 100 megabytes per second, so 10x slower. Again, we speed up the video 8x, as the video data transfer can take some time. And now that the data has been fully dispatched to each node, and each node is doing the render prep stage, which comes before casting rays into the scene. This stage involves reading the scene data, tessellating the geometry, and constructing the BVH, which is a tree structure of all the geometry in memory. After finishing the render prep, we start immediately sending the image back to the client. I'm a little bit ahead, there we go. And we are now in the MCRT phase of tracing rays. It starts off noisy and refines as more samples are returned and pixels are converged. During this MCRT phase, the gray bar is showing very heavy texture accessing on disk. Each node requires 100 gigabytes of texture cache for this size of a scene. Again, we speed the video up by 4x to move it along a little bit. And I want to note that we've implemented what we call multiplex pixel sampling here, so that we are not dependent on all nodes performing well or even being up. Whoops, I don't want to go there. I wanted to stop that. Let me get back to this. Yeah, the multiplex pixel sampling, we're not dependent on our nodes performing well or even being up in order to complete the image. If a node or a nodes goes down, the picture will still resolve, but at a slower pace, as the remaining nodes will need to take up the extra samples to be calculated. Because of this strategy, we do not see a checkerboard effect that would happen if we sent specific tiles to nodes. Let's see if I can pause it. It's going to come here in a second. Pause it there. So we have several different telemetry overlay panels already, and more are going to be added in the future. Here you see another panel, and this one is a view of the core utilization per node. And you got a little bit of a preview, but that is my presentation. I'd like to thank you for your time today and allowing me to show a few of the key advantages and utilities that demonstrate the scale and the power of the Arras computational framework and how we use that, in our case, to accelerate our rendering and create new workflows for animated feature film production. And we're excited to see how others in the community can leverage this kind of computational framework for even greater things. Thank you very much. Thanks, Canonical.
Any questions for Randy? Put your hand up.
I will do my best to answer the questions, but as I took this over from my colleague, softballs are always appreciated.
Hello, thank you for this. My question is in terms of workflow. You showed the demos that you showed. From what I understood, they are about an artist actually developing a frame and seeing what's best, etc.
Yes.
And that is using arys. Do you also use arys for the final render?
Yes, we have used arys for the final render to basically scale up the speed to get frames back. I'll give you a clear example. We have to render posters for our movies, and we had a poster. I think it took about 6 hours to render, and the marketing team decided it needed a little change, and they needed to do it fast, so they threw it up to Arras and got it back in an hour. I think they just scaled up the machines by 3x.
Hello. My question is whether the individual nodes communicate between them to know which pixels to render. Is that how you don't end up with like unrendered pieces in the image if some node is down?
I don't believe that the nodes communicate to each other in that way. I think the dispatcher sends it back off. And if it's not receiving the samples, or if a node it doesn't hear from it, it just distributes the samples again elsewhere.
Thank you.
More questions anywhere?
I do want to note that we use the Arras computational framework not just for rendering, but also for animation, and it was developed originally to handle any kind of computation. So it's a pretty beefy system.
Hello, and you obviously have your server farm, and you are using cloud services as well. What is the percentage of the job you can do on your own server farm, and when you have to resolve to cloud services?
As much as possible, we do it on-prem. So we have 50,000 cores on-prem, and we have a number of, at any given time, we have about 4 productions in progress, and they somewhat stack each other over the course of the production. A single production takes about 4 years to complete. If there's some massive push maybe for a trailer to get done, and we don't have the capacity because the farm's already fully utilized with all the other productions, that's when we go into the cloud.
Hi, me again. Is there some sort of quota mechanism to avoid one developer from taking over all the cores that are available? How do you control that?
I'm sorry, can you repeat?
Is there some sort of quota mechanism to avoid one workstation or one developer or one team from taking over all the cores you have?
Yes, we have a scheduler that sets the size of the pool given who it is that's actually using it. So a junior artist or an intern that just comes in cannot take over our entire farm with nodes, no.
Hi. I assume when you refer to virtual cores, you refer to CPU cores. So I was asking if there is a specific reason not to use GPU for
Yes, we don't have GPUs on our farm.
for like different capacity nodes, how does like the dispatcher measures what kind of computation workload it can send for that node to not like offset the speed of the whole render?
That's a good question to ask on our discussion forum to our engineers. I don't know the exact answer to that question. I assume that it doesn't do a whole lot of trying to guess what the capacity of the machine is. It just sends off the workload and gets it back. Whatever it gets back, it uses. Whatever it doesn't get back, it can, shuffle off to other machines.
Excuse me. Is there any scrutiny related to what is chosen for the next project? As you said, it takes 4 years. Is there any scrutiny related to the technical issues of what a project might require to choose which one you pick?
The scrutiny, I believe, is really on the story, the kind of story that they want to tell. And when a project does get greenlit, then the production does go into a mode of a little bit of research and development and figure out, okay, do we have the technical tools that's going to help us achieve this look? Or do we need to develop something? Or do we actually purchase something? So there is a whole phase at the beginning of a show that actually is called look development, which is a lot of experimentation of like, okay, this is the story we want to tell. This is the look direction that we've been given. And this is the technology needs of the show. So each show could have slightly different technology needs.
Any last questions? I have one. Why not purchase GPUs? Too expensive?
I'm sorry?
Why not purchase GPUs?
Why not
Why
purchase?
not? Yes, GPUs.
Purchase, our artist workstations do have GPUs, and MoonRay itself runs as a GPU solution, so it can access and process some rays on the GPU. For the farm, our scenes are very, very large. I mentioned that if for a production level scene, you have about 100 gigabytes of texture cache that you'd have to stick onto the VRAM. You have the scene itself, not just the textures, but the scene itself is about 200 gigabytes large. That level of CPU would be pretty cost prohibitive to make a movie. Maybe someday they'll get there. Everybody's excited about that, I know.
I have a question. Like, do you have some kind of caching mechanism in case some pixels do not, the values do not change after changing the light position or something, or does Arras do the computation for every pixel in every
I
frame?
think we send out the pixels to all the machines and get them back as they come. We do some caching, for instance, on the textures. If we're doing multiple frames, we'll try to load them up in order on the same machine, so we have hot caches going on there. Yeah. Read the scene data, get it into a hot cache for sure.
Okay, I think it's the end of the session, except if there's any, probably have time for one last question.
Oh, these are great questions. I really appreciate it.
Soft enough?
Oh yeah, no, that was fine. That was fine. I can cover that.
Awesome. In that case, I'll let you off the stage. Thanks a lot for your presentation.
Thank you, everybody.